Thank you so much for coming back. Sorry for the short coffee break. Our next speaker is Mark Ryan. Please, goodbye, Mark. Thank you.
Thank you. Good morning. Good afternoon, everyone. So I'm Mark, and thank you so much for Rajesh and Azalea for inviting me today. I'm a little bit outside of this community, although I think the talk is well within it. So I want to tell you a little bit about transparency protocols. So I'm going to introduce what they are first, and then talk about the automatic verification of them, which is kind of more what this community is interested in, perhaps. So transparency protocols, if I get rid of the full screen. Yes, it's gone. Transparency protocols are protocols whose actions can be publicly monitored by observers. So observers may be relying parties, people within the protocol, or regulators, rights advocacy groups, general public, and things like that. And I'll come to some examples in a moment. And then actions are typically, in this context at least, the usage of private keys. So private keys are used for decryption and for signing. But those are the actions that we want to make observable. And just to give you some examples that at least the first one you'll certainly have heard of, cryptocurrency is an example of a transparency protocol because you can't secretly spend money in cryptocurrency. That's the whole idea of the blockchain. Because if you could secretly spend money, then you could secretly give £1 to somebody, the same pound to somebody else. You could double spend, in other words. So the way that cryptocurrency avoids that is by making the spend action observable by everybody. So nobody will accept that I've given them money unless it appears in the blockchain, unless, in other words, it's publicly observable. Certificate transparency is another transparency protocol because you can't secretly issue certificates. The idea of certificate transparency is that your browser will only accept a public key certificate if that certificate is accompanied by a proof that it's in a log, in the certificate transparency log. Hence that prevents governments like the Iranian government. There was this episode a few years ago where the Iranian government issued public key certificates in order to spy on people's internet connections. So they issued certificates that claimed to be Microsoft certificates or Google certificates or whatever. And the idea of certificate transparency, you can't secretly sign certificates. And now the third one I want to tell you about, and I have a slide about it in a couple of minutes' time, is something that I'm very fond of and that I think really ought to get more attention, and that is transparent decryption. I want to have a protocol in which you can't secretly decrypt stuff. So this is quite counterintuitive because you might think, if I have the private key, the decryption key, and I have the ciphertext, then how can I make the action of decryption observable by others? I mean, I can just privately apply the private key to the ciphertext and hence obtain the decryption. Well, so I'll come to how we might do that. But the idea is that you want to have transparent decryption. The use of a decryption key becomes a publicly observable thing. I'll come back to that and exactly how one might do it. So how is transparency achieved? Well, all of the protocols I mentioned have the same idea, and that is they have an append-only ledger which records the events that are required to be observable. And then the idea is that observers can look at that ledger and see what events have taken place there. And if they're denied access to the ledger, well, at least they know they're denied access because they tried to look at it and it wasn't there. So they can blow a whistle, complain or whatever. So how do you ensure that events really do get recorded in the ledger? Well, in the case of certificate transparency, as I mentioned, your browser accepts a certificate only if it's accompanied by a proof. So we could think what that proof involves, and I'll come to that in a moment, but by some sort of proof of presence in the ledger. And then cryptocurrency, a payee, a receiver of a payment, accepts that a transaction has taken place only if, again, they can see that it's there in the ledger, in the blockchain. And now for certificate transparency, we want that to work in a similar way, but we need trustees, and that's the bit of it that makes it a little bit different because Here we're talking about a decryption key. So the idea is that there will be trustees that hold shares of the decryption key. They don't get to see what's being decrypted. They don't get to see the plain text, but they do get to, they perform what they're trusted to do. And the reason they're called trustees is that they perform the decryption only if the request is accompanied by a proof of presence in the ledger. We have the same idea that there's a ledger, it's publicly observable, and the action takes place only if that thing has been correctly recorded in the ledger. I'm going to come back to that. So let me just say a little bit more about what these proofs might look like. So let me just go back to the first example, certificate transparency. That's where your browser only accepts a public key certificate if it's accompanied by a proof. And there the ledger is organized as a Merkle tree. So you probably already know what a Merkle tree is, but it's a list of things. Here R1 to R6, R7, it grows to the right like that. And then it's a tree, obviously, and then each non-leaf node is a hash of its children. So H12 is a hash of H1 and H2, and H2 is a hash of H12 and H34, and so on. And then you append to it by growing it to the right. So when you introduce R8 now, then R7 will drop to the level below, and then R8 will be there. When you introduce R9, you'll make a new root, and then there'll be a single sort of branch going to R9, and then that part of the tree will fill up, and then you've got 16 such things, and you have to make yet another new root and so on. And the idea of that, it's really similar to a hash chain, but it has the advantage that the size of the proof of presence. So if I want to prove that R4 is in that tree, all I have to do is give you one hash value per layer of the tree. In other words, this thing, the size of the proof is logarithmic in the size of the entire tree. And the time to verify such proof is also logarithmic. So that's the idea of a Merkle tree in very short. Now, cryptocurrency, for various reasons, didn't adopt that. They adopted hash chains, which are a very similar thing, except they're not logarithmic, they're linear. So it's not so efficient. And then transparent decryption, well, there we have Merkle trees again, so we have the logarithmic size, but of course we have these trustees, as I mentioned as well. That's just a little review of some protocols. Now, I want to just mention a little bit more about transparent decryption as the third of those three examples. As I mentioned, transparent decryption relies on a set of trustees that hold shares of the decryption key. Shares because you don't want any of the trustees to have the full key, because you want to distribute the trust among the trustees. And ideally, they hold that in hardware. And ideally, it's held in hardware and bound to a program. In other words, it can't be used arbitrarily. It can only be used by that program. And that program is going to verify that the proof of presence in the log accompanies the decryption request. So we'd like to achieve that binding of a decryption key to the binary that verifies the proof of presence in the log. And then that will increase the security. And therefore, you could imagine that this could be done by a TPM. That's a TPM there. Of course, that's not one of the protocols that TPM offers. So this would be TPM++, if you like. Or maybe it would be something like OpenTitan. Titan is the Google chip that offers TPM protocols, but a superset of that, so others as well. OpenTitan is an open source project for further extending that. Or you could imagine it being done in Intel SGX or another confidential cloud computing kind of platform. Or you could imagine it's being done on a Raspberry Pi that's located in the trustee's office or house or something. So you have the trustee is distributed geographically, and everyone's just got a Raspberry Pi in a corner somewhere that's kind of monitoring the ledger, checking the proofs of presence, and doing their part of the decryption. So that's how transparent decryption works. But now, let me talk a little bit more about the verification of these protocols and the challenges there and how we resolve those challenges. Well, this was done in the context of a system called ProVerif, which probably several people know. It's been in continuous development for 21 years now, since 2002 was its first release. And it's a software tool for verifying cryptographic protocols in the so-called symbolic model. So as you may know, verification of cryptographic protocols is either done in the symbolic model or in the computational model. And this is in the symbolic model where you assume that the cryptography works perfectly. In other words, the crypto primitives like encryption or decryption or hashing or signing, they work perfectly. You don't look at the internals of those primitives, but you focus on the structure and content of messages. That's the idea behind ProVerif. And it's been used very widely over those 20 years in TLS. That was obviously a big effort to verify that. Signal, the end-to-end encrypted messaging service, noise, avionics, voting, and many other examples. So that's ProVerif. And in ProVerif, it's a so-called push-button technology. The idea is that unlike some systems like Coq, for example, where you have to interact heavily and kind of do a lot of work yourself as a user, the idea of ProVerif is that you just kind of define things and then click submit or whatever, and it goes off and performs the verification fully automatically. So here's a little ProVerif script, and it just illustrates the crucial things you need in ProVerif. You need to define an equational theory which says how the cryptographic primitives work. So this one is saying that if you decrypt something with the secret part of the key, that thing has been encrypted in the public part of the key with a certain random, and the plain text is M. Well, after doing the encryption and then the decryption, you get back to the message itself. And then here we're interested in a query. We want to know if the attacker knows these two values or could get to know these two values. And then we've got a process which describes how the protocol works. And then ProVerif goes and works out whether the attacker would be able to get those two values or not. That's the idea of ProVerif. So as I say, you build a model of the protocol, you type in the queries of the protocol, you submit all that to ProVerif, and it either tells you that the properties hold, or ideally it comes up with a counterexample. And of course, it's doing something that's in principle undecidable, and therefore it might not terminate. It might also come up with false counterexamples. So they might not actually be realizable counterexamples. That's something that you then have to worry about. Well, the way ProVerif works then is it takes the equational theory that you wrote down, the protocol description and the queries, and it translates all those into horn clauses. And then it does reasoning about the horn clauses and comes up with the proof or counterexample. So that slide just kind of illustrates, for example, if you type in this equational theory, then it says, well, if you know the three inputs to the encrypt function, then you can apply the encrypt function. The attacker knows the three inputs and can apply the encryption function. And if the attacker knows the key and the ciphertext, then it can derive the underlying message and so on. And then ProVerif kind of works out whether that holds or not, whether the query holds for that particular protocol. So, I mean, you might think, okay, well, that looks straightforward. We can use ProVerif. There we had an example of a transparency protocol. It used either a hash list or a Merkle tree. So we just need to kind of put all that together. And that was indeed the first approach, the obvious thing to do. So we defined, for example, in the case of hash lists, also in the case of Merkle tree, what a proof of presence would be, and then how you would verify a proof of presence. So in ProVerif, you can also write down horn clauses directly, and that's the approach that we took here. We defined a user-defined predicate, verified proof of presence, and then wrote down the axioms that you would need in order to encode how to verify that proof of presence. And it all looks right, and you would expect that to work, but unfortunately, it didn't work. It didn't terminate, or it produced fake counterexamples. It just seemed that that kind of monolithic approach was not working. And I think that kind of draws attention to one of the limitations until this work of ProVerif, that you could only do these things in this kind of monolithic way. You could just define this enormous protocol with like loads of axioms, and then you push that button and you just wait. And of course, if it takes several hours, you don't know if it's about to terminate or not. At some point, you have to give up. So it just seemed that one of the things that's needed is a way of getting ProVerif to do something more like compositional reasoning. You don't want to have these monolithic things. You want to kind of do things in a more compositional way. So that's one of the challenges. There are some other challenges in ProVerif, which people who have used ProVerif might recognize. One is persistent state. One of the historic things that ProVerif has not been good at is protocols that have persistent state. Persistent state means that when you engage with the protocol, you're not starting afresh each time. You're starting from where the last session left things. And typically pieces of hardware will have that kind of persistent state because they have memory and you can put things in their memory. And then when you engage with the system for the second time, it will depend on what happened the first time. And another aspect is exclusive pathways. Sometimes you want to say that this particular pathway can only be taken once. I've got an example of that. And then, of course, modeling these big data structures like Merkle trees. That's another challenge with ProVerif. So over the years, some of these things have been addressed. Like there was this very good work, not anything to do with me, in 2022, where they introduced axioms and lemmas and restrictions in ProVerif. So an axiom is an assumption which ProVerif can be doing the resolution. It's not a clause. This is, in case anyone has heard of axioms in ProVerif and has been confused by them. I was confused for a long time when I came across them because I thought, okay, axioms, well, ProVerif deals with horn clauses, so they look like horn clauses, they probably are horn clauses, but they're not. They are used to prune the set of clauses during saturation. So ProVerif works with this saturation model during resolution, and axioms are used at the level of kind of handling that set of clauses that are being saturated at any time. Now, the work that we did was to extend this notion of axioms and lemmas to work with user-defined predicates, to work with the kinds of predicates that we want to use when we're defining Merkle trees and hash chains, and then also to provide a new methodology to use ProVerif in a compositional way. So I'm just going to very briefly talk a little bit about that. Well, here, this illustrates the way it works. Instead of just having this kind of monolithic setting where you build a model of the protocol and you have the queries and you submit it all to ProVerif and you get an answer back from ProVerif, it works in a more compositional way. But you can say that I want to use a particular kind of data structure. So I'm going to verify the properties of the data structure independently of the protocol that's going to use them. So you build a model of the data structure. Then, interestingly, the null process, because you're not talking about any particular protocol using the data structure, just the data structure itself. And then the queries about the data structure. ProVerif then tells you whether the data structure satisfies the query. And if it does, you then use those queries as axioms when it comes to modeling the entire protocol and its properties. So ProVerif then takes the model of the protocol, the properties, and the axioms about the data structure, and then tells you whether the protocol satisfies the properties or not. So that's very nice because finally you can do things in a compositional way. You can say, I just look at the data structure and prove its properties, and then use the fact that I've made that proof when I come to reasoning about the entire protocol. That's our main contribution there. So I think that's my last but one slide now, just to mention the results then of that work. The results are in two parts, I think. The first is ProVerif itself. So we extended ProVerif to support arbitrary predicates in axioms and lemmas. Proved soundness of that extension, programmed it as well as proving its soundness. And then, yes, as I mentioned, implementation of the extension will appear now in the future release of ProVerif. And then as far as transparency protocols are concerned, we proved properties of the data structure, so proof of presence. Another kind of proof is proof of extension, because when you're talking about these append-only ledgers, you want to be able to process a proof that the last time you saw the ledger, that the current time you see the ledger is an append-only extension of the last time you saw it. In other words, since the last time I saw the ledger, the only thing that has happened to it has been appendings, not changings of what was there before. So correctness of the proof of extension, sensitivity of proof of extension, and then the interaction between those two types of proof. That's also one of the things that we were able to show there. And then finally, the ProVerif code for the two examples we chose in that paper, which are certificate transparency and transparent decryption. So that's it. ProVerif is still in active development, and these features are now being built in. So that's very nice. But really, I'm very interested and would very much like to have more conversations about this idea of transparency protocol. I don't think that name has been given. Obviously, these things have existed before, like certificate transparency and cryptocurrency. Those are obviously years old. But I don't think people have given this name to that type of protocol, transparency protocol. But I think they're very, very interesting. Transparency of signing and decryption is what I focused on in this talk, but there's transparency also of data handling more generally. How could I know that my data uploaded to the cloud is being handled in the way that I expect, in the way that meets the privacy statement of the company concerned or whatever? So transparency of data handling more generally. And then, of course, the big one that's been mentioned a few times already with various terminology, transparency of AI or understandable AI or whatever you might want to call it. I think that's also a very interesting idea, that we want these computations, we want to build ways in which these sorts of computations can be more observable by people who are affected by them. Thank you for your attention.
Excellent timekeeping. So are there any questions for Mark? Yes.
Mark, I know you mentioned that you have a soundness proof of this. Could you give us like a broad idea of what is the soundness property that you are after in these kind of protocols, transparency protocols?
Okay, so the soundness that I mentioned is not about the protocols themselves, but just about whether the verification computation, the verification algorithm could produce fake proofs or not. So that I can't comment on straight off because I don't know. But maybe your question was more about the soundness of the protocol itself.
Yeah, when would I say that a protocol is transparent? Actually, what's the soundness criteria? Or we can also take this offline if you.
Yeah, it's an interesting question. I mean, I think just as a quick answer, I just want to come back to you have this ledger, and then you want to be able to see in the ledger that something happened. So the soundness means that if the ledger says that somebody spent money, then they really did spend it. Or if the ledger says that this certificate is a valid certificate, then it really is a valid. But I'd be happy to talk about that.
Yeah.
Sophia, you have a question?
Yeah, I have got actually two questions, if I may, you can choose. One is, you spoke about these three examples, and then you spoke about the different ways of doing the ledger. I would have thought that there would be an interface between the ledger and the properties, and whether you use a Merkle tree or a hash chain, you could have the properties. The protocol should be blind as to how the ledger is implemented. That's my first question. My second question is, you said transparency of AI, which sounds wonderful, but I would have thought ProVerif is totally the wrong tool, because it assumes that we have got a protocol, and AI doesn't have one of the most powerful current versions, have no protocol. They're a black box.
Okay, so for your first question, I completely agree with you, and that was my point really, that we don't have to worry about the details of the underlying data structure. You prove that in one place.
Okay.
So then when you come to prove the protocol, you just inherit those axioms. You don't care whether it's a Merkle tree or a on your second point, is ProVerif the right thing for transparent AI? No, of course not. And I did not mean to imply that. I just meant that transparency itself is an important tool for society, not just about signing and decryption, which is the domain of ProVerif, but about much more ambitious stuff like the transparency of AI. And of course, that goes well beyond what ProVerif can do.
Apologies if I missed it from your talk, but why might you want transparency of decryption?
Why would you want that?
Yes.
Okay, I'm very happy that you've asked that question because it's something that I feel very kind of passionate about. I think because, well, for example, a lot of people call for regulation of cryptocurrency, which I think is needed. Society does need to have rules about money laundering and so on. But on the other hand, the way that the finance industry is regulated right now is just disproportionate because everything I do is known by my bank. So what I'd like to have is that I give them the power to decrypt stuff about me, but I get to see whether they use that power or not, whether they exercise that right to decrypt or not. Then at the end of the years, for example, I could say, well, I can see that of all the transactions I've done, only 1% of them have been decrypted, or maybe 10% of them, you know, that it seems to me that transparency over how much stuff gets decrypted could in principle solve a lot of societal problems. Perhaps one very controversial area, which since we have NCSC here, GCHQ proposed a protocol called the Ghost Protocol for decrypting WhatsApp messages. The idea would be that GCHQ could decrypt your messages. And a lot of people object to that, obviously. It strikes me that transparency of decryption could help there, because maybe I would submit to my messages being decryptable by GCHQ if I was able to tell to what extent they actually exercise that right, to what extent they actually decrypt my messages. Now, of course, that comes with other problems because they may say we don't want to tip off people who are under suspicion and so on. But I still think that transparency of decryption goes a long way towards reinstating privacy rights that might be eroded by IT.
Okay, that's not, well, thanks, fine. You're the next speaker. Thank you so much, Mark.